Is there any link to?
Click start stream. That's good.
Is it streaming? Does everyone have the link?
That changes.
Did it change?
Sorry?
Do you have the link? I don't have the link.
Yeah, I'll send it on the messenger.
Okay. Does everyone who's watching the first stream?
While you guys are waiting, could you two start filling the form on the Facebook event page? I know it says for online only, but just like fill that in for attendance. The link has been sent out. Yep, okay, should be on.
Yep.
We can start whenever you're ready.
I'll just check that my microphone and everything's working for the live stream. If someone could send something in chat. It's all good, do you think? Yeah, okay. Okay, so I'm Isaiah. I'll be presenting topic 4, which is logic and proofs. And we'll just get straight into some questions. So, first one is from last term. And there's quite a lot of text, but it's pretty much just saying we have 4 people who either pass or fail an exam. We have some information about them, some clues, I guess. And for each student, and based on this information for each student, we'll determine whether they'll pass or fail, or there's not enough information. In the actual exam, this question, they gave you 8 check boxes. One of them was like, Zamina fails, Zamina passes, Yusuf fails, Yusuf passes. So 8 boxes, and you just tick the ones which were possible. So this is just the question down to its bare bones. And if you just read them, you see that one straight away. Zamina will pass, so you instantly have a free mark, I guess. So X passes. Yep. Will this help? This won't stop on the stream. It won't make the stream sound really weird. Okay.
No,
Yep.
it'll be fine.
Yep. Okay. Is that better? Yep. Yep. So that was free. And then the only other really there's one place that we clearly can go, which is the first one. We have either Yosef or Zamina will pass, and we already had the Zamina passes. Should have said, but not both. So clearly, I fails. So we've like fully exhausted these two. So that's fully exhausted, and that's fully exhausted. So we pretty much just want to see what we can get from these two. And we see that these two only involve W and Z. And I guess you could just try out all possibilities. But one clear thing is we have the conditional here, if Zoe passes. So we can just see what happens if Zoe passes. So if Zoe passes, then William will also pass. But we know that one of them will fail, so that's impossible. So therefore, Zoe must not pass. Zoe fails. Otherwise, there's a contradiction. That's awful. Okay, and then we can verify that William, if Zoe fails, then William can pass or fail. In either case, this one's satisfied because Zoe fails anyway, so it doesn't matter. For this one, it doesn't matter because Zoe fails, so that one's irrelevant. And for that one, Zoe's already failed, so we've already satisfied it, regardless of what William does. So we have that William is unknown, which was a valid response. Either works. Either is consistent. Hopefully I'll get better at writing as this goes on. That all made sense? Yeah.
Explain why Zoe fails.
Yeah, that was probably the hardest part. So, I guess, so X and Y were pretty much for free. So pretty much we only had to consider the middle two statements, W and Z, and they both don't involve X and Y, so they're kind of just a standalone question now. So we can kind of just consider all cases. So Zoe passes, Zoe fails, William passes, William fails. All four cases, we can do all four cases, or we can try and take a shortcut. And in my case, the shortcut was to say, if Zoe passes, then we get that William will also pass. But that's impossible by the third dot point, which says that at least one of them will fail. Yeah, cool. I guess as a side note, just because this question was like just an online thing where you tick the boxes, you didn't have to write any like formal working. You didn't have to write out the propositions and write them out symbolically. But we'll get onto a bit more of that later. But this is just kind of seeing how you can just apply logic rather than like notation to get the problem out. Okay. This next problem, quite a bit of text again, and this one is like a symbolic logic question, at least part A, where you have to write the negation of the given statement, and then you have to prove that a given sequence does not matches the negation or doesn't match the original statement. So it's quite common to see questions where you have to negate or find the contrapositive or something similar, or the converse to a symbolic statement. And pretty much what we do is we use these kind of identities. I don't know if these are like formally recognized, but so we have, if it's not true that for all A, some proposition for all X, some proposition depending on X is true, then there must exist a counterexample. So there exists X such that not P of X. This is very intuitive. If something's not true for all X, then there must be a counterexample. Sorry, that got quite messy. I'll redraw that. So there must exist a counterexample. Yeah, so that's just true. As I said, it's kind of intuitive. You could probably almost treat it as a definition of for all if you're given the definition that exists. And also you can switch these around. So you can change that to there exists and that to a for all. And the statement's still true. And that's saying if there does not exist a counterexample, then then it must hold for all x. And I guess if you're following that notation, you have to replace that with the colon, not with the comma. So I guess I've strayed away from the question here, but the point is that we're going to apply a not outside here. Oops. Yeah, okay. We're going to apply a not at the very front there. And what we can do is, using the second one, we can kind of suck that not in, and then it goes into there, and we flip that to a for all. And then we have for all n. For all n is an element of z. We have, so I'll write it out. For all. Still getting used to this, sorry. We have not, and then some stuff. Right? So now we've kind of sucked that not in one layer down. And we can kind of just keep applying that to as many there exists or for alls as we want. And then at the final layer, we'll get A is not even, so we'll get A is odd. A sub n is odd. So I'll erase that for room, but pretty much that's kind of the motivation behind why we can just flip all for alls to there exists and all there exists to for alls, because of these things you can kind of recursively just go down the list and flip them all until you get to the bottom layer. So the answer is for all n z there exists such that an was introduced, so the opposite of an is even is an is odd. Yep. So does that make sense how I got to that statement there? Like stuff before that was just motivating it, but hopefully that's somewhat clear. Yep. So it's a good question. The reason is, if you have these things, you can also have like a condition inside them. So you can have for all x is greater than n, for example, or less than n. It's very hard to read. Hopefully you can see where I'm going. But if we're I'll actually undo that. But if we replace this x with, if we replace this for all with x is less, if x is greater than n, so replace that with x is greater than n, this identity still holds. So you can reason about it in the same way. So you can say if for all x is greater than n, something is true, then there exists no x greater than n such that the thing is not true. So when you have kind of conditions inbuilt within the for all or there exists, they don't get negated. So the negation kind of skips the condition inside, goes down to the bottom layer, and then you flip only the bottom layer. Cool. So that might have been something that you covered briefly in class, like just flipping the signs and flipping the last one. Hopefully that motivation made a bit more sense. There's an intuition behind it. Okay. Okay, so that's what I had up before, and I guess I've skipped straight to the answer here, but after some playing around, I guess the first observation that you make, or the first thing that you see, is you can rewrite this as 837 plus, and just by fractions, you have 10 plus 4 71 on n. And so yeah, that's just from fractions. And then it's intuitive, or it's, I guess, an identity that you can take out that 10. So the floor of an integer plus something is just the integer plus the floor of that thing. 847 plus 471 on n. So I haven't really explained what we're doing here. So we're trying to prove that this statement is true. So we're trying to say for a given n, we're trying to prove that this statement's true now. So we're trying to say for a given n, we can find a little n larger such that a of n is odd, a sub n is odd. So to do that, we find a formula in terms of big N for little n such that we'll respect that. So we'll respect, firstly, that is true, and secondly, that is true. And we'll see how both of them hold as we... Actually, the first one's very simple. The first one is just by our choice. So maximum of n plus 1 and 472 is automatically greater than n, because if it was less than n, then we would have picked n plus 1. So it's just almost a definition of maximum, is it's greater than or equal to both of its arguments, or all of its arguments. So we've got down to here. So we're still trying to prove that this is odd. And the other thing that we used was that n is the maximum of n plus 1 and 472. So that means it's also greater than 471. And that means that 471 on n is less than 1, because n is bigger than 471. So something over something bigger is clearly going to be less than 1. And the floor of something that's less than 1, or I guess it's between 0 and 1, because it's positive, because n is positive. The floor of this thing is going to be 0. So that's 847, which is odd, as we wanted. So to quickly go over that again, the reason we chose this max, which looks kind of funny when I pulled it out of nowhere, was we wanted to satisfy this constraint, and we also wanted to exploit the fact that we wanted to make this floor 0 over here. You could come up with other bounds, but this is probably the cleanest one to satisfy both of them without getting very complicated. So does that whole question make sense to you guys? Sorry?
Why would we set bound? How would we know that between 0 and 1?
So we're talking about this line, right? Yeah. So remember, we're trying to prove that for all n, there exists some little n. For all big n, there exists some little n. So we chose this little n to satisfy it's bigger than n and bigger than 471 by using the maximum function. And then using that, so we have n is greater than 471, so n is positive as well, clearly. And then if n is greater than 471, then 471 on n is going to be less than 1, and it's positive, so it's going to be greater than 0. Yep. So it's just pretty much by choice. Okay. So another question where we're flipping signs. This one's a bit different. This one's not a negation, this one's a contrapositive. And I guess we'll recall that contrapositive. Contrapositive of P implies Q is not Q. This is the definition of the contrapositive. It's only can be applied to an implication or a conditional, and it is always true that if they're equivalent. So a statement's equivalent to its contrapositive. But that's not relevant to this question. We have to rewrite this thing. So if x is a perfect square, then lots of stuff. And so this bit will be our P, and then the rest will be our Q until the end. I won't underline it. So we can see that the if sign has moved here. So also this one was 2020 question 1, term 1, so it was online as well. So you actually picked an answer for each box here. But in this case, I'll just write them out. So we kind of have to follow their structure. We can't like mold it, make our own thing up. So that's why it's kind of formatted like this, because that's how it kind of appeared in the exam. So we have to negate. So we've moved the if. So we've already kind of flipped the things around, and then we have to negate each statement. So the if went from this one to this one, so the implication was reversed. So I guess in the actual thing, we'll write it as not P is implied by not Q. And that's what it means to put the if there, I guess. That might be an abusive notation, but that's okay. So we want to flip this, so this one's easy. It is not. And then we had a for all prime integers P. So remember that we can actually just flip this. So now all we're doing is finding the negation of the second part because of my contrapositives definition above. So if there exists a prime P, I'll just use shorthand because there's not much room. So we need there to exist a prime such that does not exist an even integer. So for all even integers, the thing inside will not be true. For all even, and then we need to, so we're doing our recursive thing again. So now we go down to the last layer. And our last line is P to the A divides X, and P to the A plus 1 does not divide X. And so we have that and there, which is kind of important. So to negate this whole expression, we negate each individual part and replace and with or. Again, you can kind of motivate that by intuition, or you can motivate that by the laws of logical operations. So PA doesn't divide X. And we replace and with or and divides. Okay, my writing has gotten slanted, but I think it's a bit neater, so hopefully it's good. Do you follow how we completed this question? Yeah. This one? Yeah, if. So, yeah, in the question it's written if, and then I wrote there exists a prime. So I just briefly went into shorthand for whatever reason. If there exists, I guess, a prime. If there exists a prime. Yeah. Kind of. Yeah. So we replaced for all primes with there is a prime. There exists a prime. Here's a quick side note. Hopefully I'll be able to release these annotations after the stream. And also, this question is up on Moodle, not Moodle, Maple. So if you go to the discrete maths page for Maple, that's where I found it, and that's where you can find it. And for the practice exam, you can actually check your answer, so you can check that that's all right. So, yeah, in case you want to look at it later for whatever reason. Okay. So this one, kind of similar again, we have this kind of annoying looking statement, and we're trying to find a counterexample. In this case, we don't actually have to write down the negation, which makes it somewhat nice. But I think this one, more than the others perhaps, is quite intimidating to look at. Actually, that previous one was a bit intimidating to look at. And it's kind of an interesting number theory proposition anyway, but we won't go into that. But this one looks quite complicated, so I guess I'll quickly show you what it means. And I don't think it's too hard, it's just hidden by notation. So So we have there exists x such that there exists y1 and y2, and these things might as well belong in here. So it's pretty much saying there exists an x such that for all y, so we have y2 is greater than y1, and I'll rewrite that as y1 is less than y2. And we also have that y1 is greater than x, so x is less than y1, such that this thing holds. So for all x, there exists an x value such that for all two things that increase above it, the function will increase. So the function's bigger at the bigger value. And if you want a diagram for that, I guess. We're saying it does whatever, and then at some point it increases. So we fix some. So we're saying that there's some x value. We fix that x value, and then we have some y1, y2. And these are arbitrary. So you're trying to pick an x value such that whatever y1 and y2 are, you have that the function value here is less than the function value here. So that top one is f of y2, and the bottom one is f of y1. So hopefully that makes clear kind of what the statement is saying. I guess you don't really need to understand it to tackle the question, but sometimes just stepping back and trying to understand what it actually means can be useful. Okay, so if we want to disprove the there exists statement, usually, I guess before we were more commonly disproving for all statements by finding a counterexample. In this case, we have to disprove it for all x. So we have to, for a given x, we have to find some y1 and y2 that are counterexample to it. So I guess from these two, we have y1 is greater than x because it's pi greater than x. And y2 is greater than y1 because it's 2 pi greater than y1. So I guess that difference is pi. That difference is 2 pi. So we've satisfied that by choosing these y1 and y2. And now we have to show that f of y2, we have to show that this is false, because then we'll have a counterexample. And f of y1 is just cos of x plus pi. F of y2, we write this even shorter, but f of y2 is cos x plus pi plus 2 pi, because 1 plus 2 is 3. And cos something plus 2 pi is just cos of something equal, and then assert that that meant they were not greater than, one was not greater than the other. I don't think it's a bit harder to come up with a counterexample in this case, but I think if you follow it eventually increasing intuitively, which just means it doesn't increase ever, then it's quite clear that this function is not eventually increasing, just because it has a period of 2 pi, so it will not be monotonically or strictly increasing at any point. Are you happy with that working?
How does that prove the question?
Yeah. So in this case, it didn't ask you explicitly to write down the negation of that statement. I could write it down. I could write it down right now, in fact, but I won't because I'm really bad at using the pen. It'll take a while, but
So that
yeah.
proof there is good enough to answer the question.
Yeah, I think with that line written at the top there, it's good enough. So get with the line for a given x is greater than null, because that shows understanding that you're trying to find a counterexample for all x. Yeah, and then at the bottom, I guess you could say we found a counterexample. Or for all x, we are able to find a counterexample. Therefore, the statement is false. Sense. But if you want, you could write the negation out. It might even be clearer in an exam. It takes a bit to write out. And I think that's quite followable. Anyway. Cool. Okay. So, if you remember back to the first question, we kind of had a similar thing where we had some chunk of English text and we had to reason about it logically. In this case, we're lucky or unlucky, depending on how you look at it, that we have to express the above argument in symbol form. Symbol form sounds a bit weird. I'd say symbolic form, but I think I copied and pasted it, so don't commit. So if we look at this argument, we can see that there's kind of three main ideas. One is I buy a new car, or I will buy a new car. One is I'll have to give up eating out. And one is I'll have to give up seeing movies. So we need to introduce some notation. So we'll say C is I buy a new car. E, I will give up eating out. M is I'll give up seeing movies. Yep. So now it's just an exercise in do you know your notation? Or I guess the whole exercise was do you know your notation, for part A at least. So if I buy a new car, C stands for car. That's why I did it. If I buy a new car, then I have to give up eating out. And I'll have to give up seeing movies. And so the argument is that this is true. So this is not super clear in the question, but given the phrasing, we think we're saying that this is definitely true. And we're also saying that the next sentence is true. If I have to give up eating out, then I won't give up seeing movies. So if these two things are true, and then the actual argument that we're trying to test whether it's true or not is if this thing correctly implies that I will not buy a new car. I guess I'll put big brackets or square brackets. E and not M. Some extraneous brackets crept in, which don't actually matter, but okay. I think that was fairly straightforward. Yeah. Yeah. So, can you see the definitions? Okay. Yeah. So you want me to go over this part again? Yeah. Yeah. It's not your problem at all. So I was trying to clean it up. So we have C implies E and M, and then we're kind of given in the question. There's like an implicit and between these two. So we have and. That's not and, that's or. Yeah, so E implies not M, and that all together we want to ultimately show that this argument is valid. So the argument is that this whole thing implies that I'll not buy a new car, I'll not see. Okay, yeah, I had it on the next slide anyway, so I had that written out. Yeah, I was about to say that, but I said it a minute too late. But yeah, should be exactly the same as what I just wrote. So now we have to show this is logically valid, which isn't very fun. We're just kind of manipulating symbols and stating laws, but we'll do it. So we'll start with the left-hand side, I guess, and we'll use our laws of, I don't even know what they're called, logical manipulation, to get this to be true. To get this, to show that this implies the right-hand side. Did it freeze? No. Oh, I'm clicking the button. So we'll just rewrite that first bit out. And then one good first step to take if you're kind of stuck, or if you're not stuck, whatever you're doing, is probably to not use the implication symbol, just because it's equivalent to something without an implication symbol. And there's very few laws that you're expected to apply on a statement with an implication symbol. So we'll just get rid of them. And we want to use the identity that, or the definition that A implies B. A, that's an arrow. A implies B is equivalent to either not A or B. Maybe that does need a bracket. Does it need a bracket? I don't know how well defined the order of operations is in this thing, but we'll just do it like that to be clear. So that's the definition of an implication. So we'll apply that to both implications. So not C or E and M. Or not E or not M. This is by the conditional definition, which I believe you can write as conditional, just as conditional. And then, so these imply each other. It's a law of equivalence rather than inference, so we can say that they are equivalent. So our next step, maybe this part, maybe it's not as obvious what to do here, but we're kind of trying to get to not C in the end, trying to get to that. So I kind of want to see how can we get rid of, or at least simplify stuff involving E and M. And in this case, E and M and not E or not M are very closely related. They're actually negations of each other by De Morgan's law, if you want. So we'll make that explicit by replacing this with not E and M. So not E or not M is the same as not E and M. And that's De Morgan. Because we're running a bit slower than I would like, and just because I'm very slow with the pen, I'll just cheat there. Okay, now we have this E and M here and this E and M up there. So now we kind of want them to get them together, and we can do that by distributing this thing over the two things inside there. So we'll use the distributive law, not C, and not E. And we have or E or M, E and M. And not E and M. And this is by distributivity. Okay. Didn't really help that I didn't write that out. I'll just quickly write it out. I know I'm getting better at this. Yep. So we distributed that. I guess the analogy is multiplication. So we multiplied that by that. Put an and in the middle there. Then we multiplied that by that. Put an and in the middle. So now it looks way longer, but this thing is actually very easy to handle because we have this thing is true and this thing's not true, which is obviously a contradiction. So I'll now use the dittos. So I think negation is the one that they like. Contradiction probably is fine as well. So that's again a double implication. Something or something false. This thing is never true, so the first thing must be true. So we have not C or not E and M. We don't need these brackets. And then so that thing was double implication. And that one will be an identity because applying and false or all false to something doesn't change it. And finally, we wanted to prove that not C, and we've actually gotten there because if these things are both true, then the first one's true necessarily. So this one is the only single implication. So I guess note that that one's different to the rest. You can't really see it, especially with my messy writing, but that's important. That's a single implication because this one clearly doesn't imply this one, whereas this one implies all the way up. So, and that one is called specialization. So kind of reducing our space, reducing our precision, and specializing in on one half of it. Yeah, it's very messy. I've kind of just worked through it. Is there any parts that look dodgy or any questions about that? Cool. Induction. Fun. It's the simplest or the simpler induction questions ask you to prove an equality. This one's an inequality, which I think generally makes it a little bit hard. So let's straight into it. The base case, we want to prove it for all integers n is greater than 2, greater than or equal to 2, so we start with n is 2. And if n is 2, then on the left-hand side we just have 1 plus 1 on 4, which is 5 on 4. And if n, and on the right-hand side we have 2 minus a half, which is 3 halves. I guess that equals 6 fourths. So clearly that's greater than that. So we've proven the base case. I've written that up very... You'd probably want to put a tiny bit more detail into exactly how that proves the base case. If you're writing that out properly, but I've just done that to fit in a line maybe. So I think there's a few ways of setting it out. The way I set it out, probably because that's how they taught it in high school, was we assume the inequality for some specific value of n. In this case, we'll call it k. So we assume the inequality for n equals k. So we've just rewritten it but written it as k to show that it's just this one instance of this being true rather than being true for all n, because we're kind of using this n to mean for all n. So that's my notation. And then one thing you do is next state what you want to prove. What we next want to prove is that this sum, or this thing's true for k plus 1. So we want to prove this is true for n equals k plus 1. And we can write that out if we want. But what I'm going to do, because it's a bit quicker, and because this one's simple enough that you can get away with it, is we'll just go straight to what we're going to have on our left-hand side, like so. So on our left-hand side, we're going to have this sum plus 1 on k plus 1 squared. So we've just added 1 on k plus 1 squared. So this directly implies this. And we can see that this is already what we want to have on our left-hand side. So now all we have to do is manipulate our right-hand side to get it to our desired form. And our desired form is 2 minus 1 on k plus 1. So we haven't even said that we're starting our inductive step. We just kind of jumped in. And I think that's completely fine. Perhaps it's slightly unclear, but since it's such a relatively simple example, I'd be happy with it. So now we just need to manipulate this. So to try and get it to this, it's not obvious. I mean, it's somewhat obvious straight away that this isn't actually equal to this. So we'll actually have to show that this is greater than this, or this thing is greater than this thing. So that means that 2 minus it is less than this. So we can eventually get a less than somewhere down the line. So now we'll just start manipulating it and seeing where it ends up. So first thing, our common denominator, since we have two fractions added together. So that right-hand side is equal to 2 minus k plus 1 squared. I've been reading the chat a little. Okay, I think other people are handling it. So we have a common denominator of k plus 1 squared. Yeah, so we've just multiplied this one by k plus 1 squared on k plus 1 squared, and this one by k on k, and we've got into that. And we've also taken the minus in there. Why not do everything in one step? So we want to get to this form. So I guess there's two main ideas that you could look for. One of them is we have this minus some other stuff or plus some other stuff, or we have this thing times some stuff. And in this case, we can kind of see we have a clear factor of 1 on k plus 1. So we'll take that out and use it. So we'll take that out, and we'll see what happens inside here. Inside here, we'll have k plus 1 squared minus k. So it's k squared plus 2k plus 1 minus k. So it's k squared plus k plus 1. And on the bottom, we've taken out that factor of k plus 1 out to the front. So we'll have k times k plus 1, or k squared plus k. Now, this looks good because this thing is bigger than the bottom. So that means this thing is bigger than 1, which means this thing, which means if we change it into a 1, which we ultimately want to do, right? We want to turn that into just that. If we turn that into a 1, then we'll make it smaller. So we'll make this whole thing smaller here. And since it's minus, it'll make the whole thing bigger. So that means if we replace it with 1, then we've made the whole thing bigger. So we can write this is bigger than the previous thing. And that's actually all we want. Maybe you want to write it in words, exactly how this leads to that, but I won't because I've just verbally done it. And I guess to conclude, we can say, hence, it is true for n equals k plus 1, and then by induction it holds, and by induction everything holds. Yeah. If you're very used to like the classic technique of writing out your inductive hypothesis, then writing out what you want to prove, and then going back and trying to go out to prove it, like by substituting in your hypothesis into the thing, this thing might look a bit new to you. But as you can see, it's probably shorter than almost any other thing that you could possibly write, I think. Or, yeah. So it's probably the shortest general way of tackling an induction proof. That's not too hard. We'll get into a harder example later if we have time, which is looking a bit low. Okay. This one is kind of weird, so are there any questions on that? Okay. Do we want to finish? Sorry? I'm on here. Let's find a fun one. Okay. It's okay if it takes 10 minutes. It's going to be hard. Yep. Okay. We're skipping lots of content. I guess we'll quickly look at that one. We'll ignore this stuff, but actually we won't quickly look at it just because this is something that you can look over. You can Google it, I guess. But one quick thing is that probably the hardest part of the proof is to justify that. But maybe after the workshop, you can look at these few remarks down the bottom here. You can either do 13 cases, mod 13, or you can prove it very, very elegantly and, well, it's not really elegant, but it's very short with that argument there, which isn't fully cleaned out, but as an exercise you can justify every step to yourself. Okay, it's time to skip to Isaiah's question, the best question. I'm Isaiah, by the way. So, part A is given that some stuff, we want to prove this identity. Now this one is not really relevant to the course, but it's kind of used in the next part, so we'll just do it very quickly. So there's kind of two main identities involving cos x, and we have that squared, so we kind of see we're going to use that squared somewhere. So we can use the Pythagorean one, but in this case it's not the one we want. The one we want is the double angle formula, or equivalent to the half angle formula. And just going to get straight into it. This thing here, which is kind of obvious from the graph, implies that that thing is true. X squared is greater than sine squared x, and then we can ignore that because we've squared both sides. So stuff's automatically positive. So in fact, it's possibly better to do sine x squared. I think that works just as well. So actually, no, we won't do that. We'll do x squared is greater than sine x. Okay, and then we can decrease this thing by increasing sine squared x. So we can change this to 1 minus. So we use that thing from part A squared on x on 2 rather than x. And then that implies, well, that is equal to 1 minus half x squared. Just by squaring that, so you get x squared on 4 times 2, which is half x squared. So that's part A all done. Not really relevant, as I said. So part B is more interesting, much more interesting. Prove by induction that for all positive integers n, this identity, which looks kind of like a more general form of that, is true. And in particular, we have a power there and we have a multiple there, a multiplicative factor. So we'll get straight into the induction. So our base case is n equals 1. N equals 1 is cos x is greater than or equal to 1 minus half x squared. And that we've already done that in part A. Okay, did nothing to solve the base case. Now we get onto the inductive step. So we assume that it holds the sum k. So we assume cos x to the k is greater than or equal to 1 minus half kx squared. For some k is greater than or equal to 1. And we'll mold this into the thing for k plus 1. So for k plus 1, it's cos x to the k plus 1. So we want to show that this is greater than or equal to this, but with k plus 1. So we'll just go straight into this. And if we want to use, we always want to use our assumption in our inductive step. So we want to rewrite this as something that can use our assumption. So we'll go to that. So that's times. Okay. Now, these two things, we want to kind of turn them into a polynomial in x. So they're not very useful at the moment. So what we want to do is turn each of them into a polynomial. We can turn that one into a polynomial using the assumption, and we can turn that one into a polynomial using the base case, or the identity found in A, which will happen to be the base case. So we'll do the base case, we'll apply it to this one first. So we'll say this is greater than or equal to cos x to the k times part A. So just applying part A there. This is greater than or equal to, we'll apply the inductive step now, 1 minus half kx squared times 1 minus half x squared. And this is from assumption. This is a harder question. I'm running out of time, which is why I'm going fast. But hopefully some of the steps make sense. You can fill in the gaps later, maybe. Okay, and now we want to get this into this form, but with k plus 1 instead of n. And we can just expand it. And I'll just expand it all in one go. We're going to get 1 minus half. We can see that that k is going to go there, and we're also going to get a 1 from there. So we're going to get half times k plus 1 x squared, which is good, but we're also going to get an extra term from these two, so we're going to get plus 1/4 x to the 4. Now this thing is greater than 0, clearly, because there's an even power, and so that is greater than or equal to 1 minus half k plus 1 squared. K plus 1 x squared. X squared there. Okay, and that is what we wanted to prove. We've proven it for that by expanding stuff and applying, quite interestingly, we applied the base case in the inductive step, and we also applied the assumption in the inductive step. And I haven't thought about it too much, but I don't think there's a much easier way to go about getting to that result. Maybe some calculus thing, because you have a power somewhere and a multiple somewhere as well. Maybe some derivative stuff, but that wasn't too bad. Does that make sense? Or have we kind of lost track at this point? Does it look good? I've gone very fast through that. Okay, I think most people follow that. It's kind of hard to look at the chat at the same time. Okay, now I asked if you followed that, and hopefully you did. Maybe you didn't because I went fast. This is actually a broken solution. This argument is not watertight, I guess. And I'll pause for 30 seconds for you to stare at this and think about why it might not be true. Or why it's true. I assure you that I hope that it's true. I hope that that I asked you to prove something that's true. But this argument isn't actually fully watertight. So, does anyone have any ideas where there could be a mistake in this? Yeah.
Subbed in the inequality one side, but then now it's less than what it was initially, so it could be the other side would be inequality.
I think my inequality sign should be correct. Was there a particular line that?
So like, sub in cos x is greater than or equal to 1 minus half x squared, for example, and then now it's less than what it was, so it's not necessarily greater than 1 minus half x squared or whatever.
Yep. So in part, I think you're almost onto something, maybe not quite right, but in part we prove that cos x is greater than or equal to this thing, or we're told it. So cos x is greater than this thing. So if we multiply both sides by cos x to the k, it should be fine, right? So that's why the sign is the same. Does that make sense for that line? But I'll say the answer now. There is a mistake, and it's very almost right there. And it is, you can't just multiply by cos x to the k. You have to make sure that cos x to the k is positive, right? So if you multiply both sides of an inequality by a negative number, then you have to flip the sign. And we kind of just assumed that it was positive. So you're almost there. So I think that's very hard to see if you're not looking out for it. So from that, I'll write it on the new slide which I prepared. So we assumed, we assumed, if we go back, we assume that cos x to the k is positive. Clean that up. We assumed that cos x of k is positive, and we also assumed something else here. We also assumed when we went from here to here that 1 minus half x squared was positive, because we replaced that with that from a known equality, but we kind of assumed that that was positive. So we also assumed that 1 minus half x squared was positive. Now, when are these going to be true? This is true. Okay, I'll do the second one first because it's easier, or a bit easier. So the second one, this is only true when, if you rearrange it, you get x squared is less than or equal to 2. So you have x, absolute value of x is less than or equal to 2. Or root 2 rather, because it's x squared. So absolute value of x is less than or equal to 2. And this one, when is this true? Well, if k is even, then it's always true. But we want to kind of be more general about it. So we'll say, if you look at the graph for cos x, it has zeros at negative pi on 2 and pi on 2. So this is definitely true when absolute value of x is less than or equal to pi on 2. Outside of that, it may or not be true, depending on k and depending on the value of x. But we can actually prove the statement very easily when neither of these hold. And when neither of these hold, this one's bigger. So the more restrictive condition is this one. So our mistake was this. Our resolution, I'll try and finish up very soon. Our resolution is if x is greater than root 2, and this covers when x is greater than pi on 2. Then we look at our statement again. We see that 1 minus half nx squared is going to be less than or equal to 1 minus half n times root 2 squared. I won't go over the inequalities again just because we're running out of time. And root 2 squared is 2, so this is equal to 1 minus n. So our left hand side is less than or equal to, this thing is less than or equal to 1 minus n, and we've already proven the result for n, right? N equals 1. So all we have to do is do it for n is greater than or equal to 2, so that is less than or equal to negative 1. For n is greater than or equal to 2, which is all we want to, which is the only cases that we're dealing with. So we've already dealt with all the cases where absolute value of x is less than or equal to 2. So now we're just, and we've also dealt with the case where n equals 1. So now we're just proving it for x is absolute value of x is greater than root 2, and n is greater than or equal to 2. So that's why we could assert that. And then now we wanted to prove that this whole thing was less than cos x to the n. And negative 1, well, cos x oscillates between 1 and negative 1, or only takes on values in the range negative 1 to 1. So that's actually a less than something, I believe, but it doesn't really matter. So that is less than or equal to cos x to the n, as negative 1 is less than or equal to cos x is less than or equal to 1. Okay, that is a complete proof. So we've exhausted all two cases. One of them is x is greater than root 2. One of them was x is less than or equal to root 2. We proved this one by an inequality argument, and we proved the other one by induction. So this is kind of a lie. You have to use more than induction, but you use induction in part of it, so it's not really a lie. And because it takes 1 minute, I asserted that pi on 2 is greater than root 2. And you can see that from the calculator, pi on 2 is about 1.6, root 2 is about 1.4. That's clearly true. And because this workshop's on proof, I'll leave it on a nice picture proof of this result. If we draw a quarter circle there for the arc, so that's radius 1. That's root 2. That's pi on 2 because it's a right angle there. Then that is why pi on 2 is greater than root 2. That's just a random argument that fits into everything. I wanted to get onto Bruce as quickly as possible, but are there any questions about this? I was quite involved. Okay, I'm happy to talk about it after because I think I've lost some of you probably, but we'll get onto Bruce, I think.
So we'll take a brief 2-minute break. Just start 218.
All right, I think we'll start back up then. Yeah, so we just went through some proof questions, but now we'll be doing some probability and counting problems. So for our first question, it's a very common type of question where we have 5 integers, and these 5 integers have to add up to a certain number. So before we talk about that in particular, we'll actually zoom out a bit and talk about this in general. So this actually works out to be a partition question. So what we have here is we're counting the number of ways to partition some objects. So maybe we'll just think about this in general. So we have a bunch of objects, and we'll say the number of objects is A. And what we want to do is we want to split these into B groups. So what that means is, maybe let's say, for example, B equals 3. That means we want to split them into 3 groups. So in other words, we want to say, okay, so this group over here, group 1, this guy gets 3, this guy in the middle gets this number, and this guy gets the third number. So basically what we're doing is we're taking these 8 objects and we're splitting them into B groups. So what we know about this situation is that it's equivalent to, say, let's say we have these A dots. Yeah, let's say we have these A dots, and basically what we're doing is we're trying to split them into B groups. So that means we have to have B lines separating them. So we have B minus 1 lines separating them, right? Because in this case, we want to split them into 3 groups. So we need to have 2 lines separating the 3 groups. So what this comes down to is we have a number of spots. So let's say we have these spots over here to put things in. And we have, how many spots do we have in total? We have A plus B minus 1, right? Because we have to have A spots for the objects and B minus 1 spots for the dividing lines. So we have A plus B minus 1 spots, and we want to basically pick where the dividing lines will go. And we have B minus 1 dividing lines. So that's equivalent to choosing b minus 1 spots out of a plus b minus 1 objects. So in other words, if we want to partition a objects into b groups, then we can just use this formula. And if you don't really understand the derivation, then maybe you can just use this formula. Yeah, so this is our formula we use. And so how does this link to what we're talking about? Well, what we have is we have 5 numbers, and they all add up to 100. So let's just say we have 100 dots. And these 100 dots, well, we have 5 numbers that add up to them. So what we're going to say is we're going to say we have 5 groups essentially. Right, so we're separating these 100 dots into 5 groups. So in this example, this thing would be x1, so x1 would be 3, x2 would be this, x3 would be this, x4 and x5 and so on. And so what we have to do is we have to count the number of ways to basically split 100 dots into 5 groups. So we might have seen this type of problem before. Does anyone know? So in this example, we're basically splitting up 100 objects between 5 groups. So what would our answer be? So what we do, basically we have A is 100, so that means that we have C, 100, plus 5 minus 1. And then we have comma, 5 minus 1. So it would be C, 104, 4. Does that make sense? Okay. So that's our answer to our first part. And so the second part is a bit different. What we have is that there is a restriction on what these numbers can be. So they have to be congruent to 2 mod 3. So x1 can be 2, it might be 5, or 8, 11, so on. Right, point is it can't be anything we want. Then we have x2, it has the same range, and so on. And so the idea is basically we can't use the same argument. We have to try to express this in our expression for x. So what we do is we say, what's the definition of congruent to 2 mod 3? Well, in general, if x is congruent to 2 mod 3, we have x equals 2k plus 3. And so k will be our integer. And so what we do now is we basically say that it's going to be true for all of them. So let's scroll down, and we see that's what we've done over here. So for each xi equals 3ki plus 2. So in other words, for example, x1, we express it as 3k1 plus 2, x2 equals 3k2 plus 2, and so on. And so what we're going to do is we're going to split this back in. So we basically encode this equation in the question. Right, and so now what we want to do is we want to get this in its simplest form. So we'll have 3k1 plus k2 plus k3 plus k4 plus k5 plus 2 times 5, because we're going to have 5 2's. And that would be equal to 100. And so now we can simplify that a bit. We'll get 3 times k1 plus k2 plus k3 plus k4 plus k5. Well, that will be equal to 90. And so what we know is that this sum of k's is going to be equal to 30. And so now we've basically removed the restriction by implementing a new system of equations. So now our equation in k, it doesn't have any problems. So we also know we have the same situation as part 1, except now our a is different. So all we have to do is plug that in. So we get c 30 plus the number of groups, 5 minus 1, comma 5 minus 1. And so we get c 34, 4. And so that's our solution to this part of the question. So now we're going to look at C. So C, we have a bit less information because we don't know what they're congruent to mod 3. So what we can say is let's actually try to encode this by saying let's do our division algorithm. x1 equals 3k1 plus a remainder, but we don't know what this remainder is. So before we knew that this remainder was 2, but now we don't really know it. So we know it's either going to be 0 or 1, because those are the other 2 options. So what we'll do instead is we'll just write this as R1. And what we know is that R1 is either going to be 0 or 1. And so what we're going to do is we're going to do this for all of our numbers. So x2 will be equal to 3k2 plus R2. And we'll keep on going until we get to x5. And so all of these cases, we have the same range for R. And we keep on going down. So now what we want to do now is we want to sub this back in. So what we'll get is we'll actually get 3 k1 plus R1. That's going to be equal to x1. When we move on, we get 3 k2 plus R2. You continue down, we get 3 k3 plus R3. And all the way down to 3 k5 plus R5. And that's going to be equal to 100. So we can actually split these up, right? Because it's a bit complicated to consider k and r together. So we'll just do 3k1 plus 3k2 plus 3k3 plus 3k4 plus 3k5. That plus r1 plus r2 plus r3 plus r4 plus r5. Well, that will be equal to 100. So maybe let's try to split this up. And as this slide says, we'll first consider what r can be. So let's just try to consider r for now and ignore k. So how will we get information about r? Remember, r is our remainder, right? Because we're dividing x by 3 and we're seeing what it is mod 3. So we're going to consider both sides mod 3. So the left-hand side mod 3, well, that would just be this sum. That means that we know the sum of our remainders is congruent to 100 mod 3. Right, so what we have here is, because this disappears when we consider it mod 3, we just have the sum of the remainders being equal to 100 mod 3. So why don't we make this a bit simpler? We know that that's congruent to 1 mod 3. So in other words, the sum of remainders well, it can be equal to 1, it can be equal to 4, it can be equal to anything, right? It can be equal to anything as long as it's congruent to 1 mod 3. So we'll keep on going down like that. But actually we have a bit more information about these remainders. We know that they're either 0 or 1, right? Because the remainder is always going to be less than 3, and we know it's not 2. So our remainder is going to be 0 or 1. So that means it can't actually be anything. So let's consider R1 plus R2 plus R3 plus R4 plus R5. It has to be less than or equal to 1 plus 1 plus 1 plus 1 plus 1, because that's the greatest it can be. If all of them are 1, then it'll be equal to 5. So that's our maximum. But what about our minimum? Well, it can either be 0 or 1. So our minimum will be when they're all equal to 0. So we know that this sum of remainders, it's going to lie between 5 and 0. So in other words, when we look at this list that we drew up, we know that this isn't actually true because it's not going to be there, it's not going to be there. It's either going to be 1 or 4. And so that means we have a very manageable size of cases to deal with. So what we can actually do is just split these into 2 cases. So first of all, we'll say what happens if this is equal to 1. Then we'll say what happens if this is equal to 2. So to find the total number of solutions, we add the total number of solutions in each case. Yep, so as it says here, let's consider these cases separately. And then we'll start thinking about k. So let's first consider this first case. Right, so maybe if we don't know how to count how many cases there are, how many ways there are to do r, then we'll just come up with an example. So maybe one example is like 1 plus 0 plus 0 plus 0 plus 0. That's going to be equal to 1. Right, that's an example because r1 is equal to 1, all the rest of them are equal to 0. That satisfies this equation. So what do we realize here? We realize that actually we can have 1, 1, but the rest of them have to be zeros. So the number of ways to solve this equation is actually just the number of ways to choose one of these to be 1. and that would be 5, choose 2. So that's the number of ways to choose R. But we're not done yet because we have 2 things we have to solve for. Right, we have to deal with K and we have to deal with R. So let's move on to K. We know that 3K1, well, let's just rewrite our equation. This was from before. Well, that sum is going to be equal to 100. So if we're taking this first case, you know that this disappears, it's just 1. Alright, that's good. So now we know that 3K1 plus 3K2 plus 3K3 plus 3K4 plus 3K5. Well, 3 times it is going to be equal to 99. So this is 33. Sorry, this will be 99. So we're just taking away the 1. Alright, and then we can divide, and that's where the 33 does come in. This will be equal to 33. So that's a really nice case, because now we have basically a normal question. Right, we've gotten rid of the annoying thing that says it can only be congruent to 2 mod 3, or it can't be congruent to 2 mod 3. So now we have a perfectly normal question, so we just do C, 33 plus 5 minus 1, and 5 minus 1. So we get C, 37, 4. So we've talked about this case. There are this many ways to choose K. This many ways to choose R. So because K and R operate independently, the total number of ways to choose our x's is just going to be the product. So our total number of ways, let's write that at the top. In this case, it'll just be equal to C, 37, 4, times C, 5, 2. Right, so that looks like a plus, that should be a times. And that's the number of ways in this case.
I think it should be C5.
Yep, my mistake, sorry. So we only choose one, of these. Yep, so we're only choosing one of these. So yeah, that would be C51, my mistake. Yep, and that's the number of ways for this case. Okay, so the other case is quite similar. So maybe let's just try solve this. This is one example of a solution. And we realize that it's quite similar to the previous one, because we can have exactly 4 ones, and we need to have 1 0. So how many ways to choose R? Well, that would be equal to the number of ways to choose 1 0 out of 5. Which is not C52, contrary to what I wrote before, but C51. Next thing, let's consider K. So we have our nice equation. And that will be equal to 100. So now, what we know is that this thing, well, we know it's 4, because that's our case. So now we can just subtract 4 from both sides, and we'll get 3K1 plus 3K2 plus 3K3 plus 3K4 plus 3K5. So that should be a 4 equals 96. So that means this sum is equal to 32. And so we've done this before quite a few times. So we do C32 plus 4, 4. That'll be C36, 4. So how many ways can we choose K? Well, it would be this. How many ways can we choose R? Well, it would be this. So to get the total number, we just multiply them together. Yep, and so we've taken now 2 cases. Whenever we take mutually exclusive cases, which means cases that don't overlap, we can just add the total number from each. So for example, we take this and we add it to that. So our final answer, let's write that down. That will be equal to C times 37, 4 times 5, because that's just C51, plus C36 4 times 5. And so that's our final answer there. Alright, let's move on to another type of question. So here we have a situation where we have 4 separate groups of students, and those groups all have 4 students each. So we want to pick, oops, my mistake. We want to pick 6 students from the group, such that at least one of our groups has 3 representatives or more in the final group of 6. So what we might think to do is cycle through these 4 groups of students. So we have 4 groups of students with 4 students each. So let's just say we have group A has 4 students. Oops. Sorry about that. So group A has 4 students, B has 4 students, C has 4 students, D has 4 students. And the idea is, why don't we just count the number of ways for A to have at least 3 representatives in the final group? And then we'll count the number of ways to have 3 from B, then we'll count the number of ways to have 3 from C, then 3 from D, and we'll just add them all together. And that might be a good way, but when we add things together, when we add groups together, we have to bear in mind the inclusion-exclusion principle, right? Because the inclusion-exclusion principle tells us that sometimes when we add groups together, we double count. So for example, we might have a group where we have 3 students from A and 3 from B. And if that's the case, then we'll count it when we are adding this group to our tally, then we'll count it when we're adding this group to our tally. So then we'll actually double count a group like this. So what we have to do is consider the inclusion-exclusion principle. Yep, so we have to be wary of double counting, which is what we just mentioned. So what is the inclusion-exclusion principle? It means somehow we're going to have to, if we want to get the union of this set, right? So what's the union? The union is the total number of objects within the set. So for example, from before, we want to count the union of the number of combinations with 3 from A, the number of combinations with 3 from B, the number of combinations with 3 from C, and the number of combinations with 3 from D. And so the idea is we want to add these groups together, but we don't want to overcount things that belong to 2 groups. So what we do is somehow we're going to have to subtract the intersections. So what that means is, what we'll do, in this case, we'll add the groups together first. So we'll add the sizes of the groups together first. Right, so in this case, we'll add A plus B plus C plus D. And then this one is counting the intersections. So basically, the number of things that are common to 2 groups. Right, so then we'll subtract, let's say, the number of ways to choose 3 from A and 3 from B, the number of ways to choose 3 from A and 3 from C, and so on. And then we'll have to add the intersection of 3 groups. Then we'll subtract the intersection of 4 groups, and we'll keep on going until we reach as many as we can, so the intersection of all of them. And the idea is, what we do is we alternate. So we'll alternate over here. Well, first we'll add these together, then we'll subtract the intersections of 2 groups, then we'll add the intersections of 3 groups. Yep, and so we can see it written over here. We'll just add A to B, C and D, then we'll subtract these intersections, and add these intersections, then subtract this intersection. So first of all, we'll calculate the size of each set. So how many ways are there to pick at least 3 from group A? Right, so let's check out group A over here. There are 4 students here. And we want to pick 3 from them, or 4. So it says at least 3. That means 3 or 4. So let's start by saying, how many ways can we pick 3 representatives from group A? Alright, so we have to pick 4C3. That's just picking 3 from 4. What about the rest of the group of 6? How can we choose the remaining 3 students? Because we've only picked 3 students, we still have more choices to make. So what we do is we say, out of the remaining students, that would be 12 students, right? Because we have 16 in total. We have to pick 3 from them, right? So what would that be? That would be C, 12, 3. So what we know is we have to pick the 3 students from group A, then we have to pick the remaining students. So what we get So we get this product. Right, and that's the number of ways of choosing representatives, at least 3 representatives, or it's the way of choosing 3 representatives from group A. But as we said, we can also pick 4. So let's consider that. So we want to pick 4 from group A. There's only one way of doing that, or C44. And then the remaining 2 students for us to pick, we can pick the remaining 12. So we do this plus that. So that's our total number of ways of picking 3 representatives, or at least 3, from group A. So we have this over here. This is the number of ways of picking 3. And this is the number of ways of picking 4. And we evaluate that to get 946. Alright, so we've done that for one group. How many ways are there to pick at least 3 from group B? So the idea is we have the same number of students in group B, so it's going to be the same. Right, we're going to have the same number in group B, so 946. So there are 946 ways to pick at least 3 representatives from group B. Right, and it's going to be the same for group C, 946, and so on. And so that's what it says on the next slide. Right, all our sets are the same, so we'll get 3784. So remember, this is just us counting the total number. We're cycling through the groups and counting. But the inclusion-exclusion principle tells us we have to now subtract double counting. So we now have to subtract the number of groups where we have 3 from A and 3 from another group, 3 from B. Right, for example, we'll have to subtract those kinds of groups. So we've gotten this so far, which is great, but we still have to move on. Alright, so that's called excluding. So for example, let's compute the number of ways to pick 3 students from A and 3 from B. Well, is there any freedom here? Well, we can only choose 6 in total, so we can't, so when it says at least 3, well, we can only pick 3 from each group. So how many ways are there to choose 3 from each group? Well, let's think about that. It'll be C43, because we're choosing 3 from group A, for example, multiplied by C43, because we're choosing 3 from B. So this is the number of ways of picking, of double counting basically, for A and B. Right, so it'll be over here. But we have to subtract all the intersections. So let's remember our formula. So we have to subtract all the intersections of 2 groups. So the idea is, how many combinations of 2 groups are there? So how many intersections of 2 groups are there? Well, we'll have 4 groups. And how many ways are there to have 2 groups out of those? Well, that would be 4C3. C43. 2, sorry. And that would be equal to 6. So in other words, there are 6 intersections that we have to subtract. And they're all going to be the same because all our groups are the same. So in other words, well, this would be equal to 16. And to get our total intersection, we multiply that by C42, which is 6, to get 96. So this is the double counting that we have to exclude. Right, we're taking, this is our double counting. So what we do is we take this entire sum, we'll take this, and we'll get 96. So what we have to do is we subtract our number from before. That was our total number of ways of choosing across the 3 groups. We got 3784. That was equal to A plus B plus C plus D. And now we can subtract 96, which is our number of ways of double counting. Right? And so that's good so far. But now we have to move on to the intersections of 3 groups. And there's a bit of a spoiler on this slide, but the idea is, can we pick 3 from 3 groups? Well, we'll have to pick 3 from A, for example, 3 from B, and 3 from C. And already we've exceeded our quota. Our quota was we can only choose 6. So that's not okay. So this does not even exist. What's an empty set? So we don't have to consider that. We can kind of stop our inclusion-exclusion principle at the intersections of two groups. So we get 3784 minus 96, which equals this number. Yeah. So that's the inclusion-exclusion principle. I think we'll move on to this question as well. So first question, find the probability that the hand contains exactly 3 cards of one value. So maybe like 4, 4, 4. So we'll have 4 of hearts, 4 of diamonds, 4 of spades. And then we have to pick 7 cards from the remaining suit. So the remaining suit is clubs. So we have to pick 7 cards from here. So we would get, for example, 1 to 7. Alright. So a good way to start this question is what we've done here. We just do an example. Right, so one example of a valid card would be this. So to find probability, we first have to count the number of favorable outcomes and then divide it by the number of total outcomes. So first of all, we ask how many ways can we pick exactly 3 cards of the same value, and the remaining 7 cards are in the remaining suit. So in this case, we've done it for 4, and then we've picked the remaining cards from clubs. So how can we actually choose this? Well, first of all, we have to choose which value we're going to take. So how many values are there? There are 13. Right, so we could have 3 1s, we could have 3 2s, 3 3s, 3 4s, and so on. So the number of ways of picking this number over here is 13. Okay, that's good so far. The next decision we have to make is which 3 suits. So that would be 4C3. You have to pick 3 out of these. Sorry, I'm using the wrong notation. So how many ways to pick 3 suits out of these 4 suits? So that would be C43. Then we have to say, okay, this last suit is defined already, because it's the remaining suit. How many ways can we pick these 7 cards? Well, that would be the number of ways of picking 12 things, or 7 things from 12. Actually, no, sorry, not 12. We have 13 values again. So picking 7 from 13. Right, and so that's our number there. So we've basically made all the decisions we have to make, and this is our total number of cards that we want. So to find probability, we just divide this by the total number of hands. That'll be C, 52, 10. So this is our probability. Any questions? No? Okay. So let's move on to B. So how many hands are there that contain exactly 3 cards in at least 1 suit? So maybe this reminds us of the previous question, but the idea is maybe we might have 3 spades, exactly 3 spades, then we have to pick from the remaining ones. So we might have 7 clubs. So our first thought might be, okay, what we'll do is we'll say, let's pick the number, let's kind of calculate the number of ways to pick 3 spades. Then we'll add it to the number of ways of picking 3 hearts. Then we'll add it to the number of ways of picking 3 diamonds. Then we'll do the number of ways of picking 3 clubs. Right? But we might remember from before that we can't really do this unless we take into account the inclusion-exclusion principle. Right? Because we might have, for example, a hand with 3 spades and 3 hearts, right? And in that case, we've counted it twice. We've counted it in this group, and we've counted it in this group. So maybe let's do the inclusion-exclusion principle. Let's first do what we wanted to do, which is adding those 4 groups together, but then we'll remember that we have to subtract the intersections. So let's do that first. So number of ways of picking 3, exactly 3 hearts. Well, what we do, first of all, we have to pick the 3 hearts. That's C43. Sorry, my mistake. There are 13 hearts in total. So we pick 13, 3. How many cards are left? We have 39, and we can do anything with them, we just have to pick 7 from them. So we multiply that by C, 39. So that's our number of ways of picking exactly 3 hearts. Alright, then we're going to do it for clubs as well. And we'll get the same number. Because they're all equivalent. And we do it for hearts as well. Sorry, we just did hearts. We do it for diamonds as well. Same thing. Then we do, what's the last suit? Spades? Same thing. So in other words, we can just multiply this by 4. So we've actually calculated the number of ways of picking 3 hearts, then the number of ways of picking 3 clubs, same with diamonds, and then spades. Right, so that's the first part of our question done. Now we have to subtract any intersections. So our question next is, how can we pick 3 hearts and 3 clubs? Well, that's the same kind of idea. First we pick the hearts, then we pick the clubs, then we pick the remaining cards. So there are 26 left. So how many do we pick? We pick 4. Right, because we have used 6 already. Now there are 4 left. Okay. So now we know it's the same for all of our combinations of 2. So for example, 3 hearts, 3 diamonds, it would be our same number. Same number over here. So our question is, how many combinations of 2 suits do we have? Well, that would be 4C2. So we multiply that by this. Yep, and that's what we get over here. So this is our number of intersections of 2. Alright, let's move on. Because the inclusion-exclusion principle says we don't just stop at 2 sets, we continue with 3 sets. So remember, our formula was like A plus B plus C plus D minus all the intersections of 2 sets. Oops. Dot, 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 dot. And then plus the intersections of 3 minus the intersections of 4. In this case, we stop there. But the idea is we're not done yet because we've just gotten up to there. Alright, so now let's consider the number of ways of picking 3 hearts. 3 clubs. Oopsies. And 3 diamonds. Well, same thing over here. C13-3. 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 How many cards do we have left to pick? We have 10 in total, we've just picked 9. So multiplied by C13-1. Right, so that's the number of ways there. Look at this. Right, and how many combinations of 3 suits can we have? Well, that would be 4C3, which is just 4. Okay, so that's our intersections of 3 done. Now let's think about intersections of 4. So can we pick 3 hearts, 3 clubs, 3 diamonds, 3 spades? Well, we can only pick 10 cards in total, and if we do that, we'll have 12 cards. So in other words, this thing, over here, is just the empty set, which equals 0. Well, the cardinality is 0. So let's refresh what we've done so far. We've done all the calculations we need. We just have to put it together. So first of all, we do this. So this is our number of ways of summing up 1 sets. Right, so just the 1 sets, so to speak. Then we subtract number of ways of picking 2, so that would be this. One sec. Then we add the intersections of 3 sets. So we'll go down here to what we did over here. We'll get 4 times 13-1, 13-3, 13-3, 13-3. We'll add 4. And so this is our final answer, using the inclusion-exclusion principle. Any questions? Nope. Okay. Alright, let's maybe because of time we'll skip this one. We'll do the last two. So this is the recurrence relation. This is a recurrence relation question. So let's first try to understand what's going on. So an elf apparently exists. He takes 1 stair or 3 stairs. And an is the number of ways to ascend an n stair staircase. So what they want to do is ask us to find a1, a2, a3. And we can see this recurrence relation thing is popping up later. But our first step is always to find some initial values. So let's do that. So a1 equals the number of ways this elf guy can ascend a 1 stair staircase. Okay, so let's think about that. Remember, he can take 1 step or 3 steps. So can he take 3 steps at all? No, because we have 1 stair. So the only way he can ascend the stair is just 1. Right? So maybe let's take another example. Right? If he wanted to ascend 10 stairs, well, for example, he might be able to do 1, 1, 1, 3, 3, 1. Right? And these ascended 10 stairs in total. Because we have 1, 2, 3, 6, 9, 10. And this is a valid sequence. But we can only do that because we have so many stairs. Right? When we only have 1 stair, we don't really have the luxury of choice. This elf can only take 1 stair at a time. So a1 equals 1. What about a2? So a2, how many ways can he ascend a 2-stair staircase? Well, let's look at the steps. Can he take a 3-step stride? Well, no, because there are only 2 stairs. So the only way is just to take 1 step and 1 step. So this is also equal to 1. Then we'll look at a3. So we have 3 stairs. Well, he can take 1 step. If he takes 1 step, then, well, he can only take 1 step afterwards because then he only has 2 stairs left. What about if he just takes 3 steps? If he takes 3 steps, then he'll be at the end of the staircase. So there are only 2 solutions. 1, 1, 1, and 3. So a3 equals 2. Does that make sense? No, apparently not. That's okay. So the idea is, maybe let's do, so does a1 make sense? Yeah, a2. Yeah, we'll just do a3 then. So a3 is the number of ways the elf can ascend a 3-stair staircase. So if we remember our rules, this elf can take 1 stair at a time, or 3. So in other words, maybe if we want to ascend 4 stairs, then maybe we'll be able to do 3 steps, then we'll be at the end of the 3rd stair. Then we only have 1 more step to take, so it will be 3 and 1. And another way to do it would be just to do 1 step at a time. So this is 4 stairs. But let's talk about a3. So a3, what if the elf wants to do 1 step? If the elf wants to do 1 step, then he'll have traversed 1 stair. So at this point, there are 2 steps left. Does that make sense? Yep, so if there are 2 steps left, then he can't take 3 stairs in one stride, right, because then he'll be past the staircase. So the only way to do it is 1, 1, 1. There's another option, if he takes 3 steps. So if he takes 3 steps, he'll be at the end of the staircase. So then our journey is done, so that's the only way to do it. So our 2 solutions are 1, 1, 1, and 3. So 1 step at a time, or just 3 steps in one go. So we have a3 equals 2. And that's all that done. So we found our 3 solutions. Okay, so now we have to obtain a recurrence relation. So what's a recurrence relation? A recurrence relation expresses something like an in terms of previous numbers. So for example, an minus 1 plus an minus 2 or something like that. something like that. Basically, the idea is to express our term in terms of previous terms in the sequence. So this is not our answer, but that's what a recurrence relation is. So the way to do this is think about our n-stair staircase. So let's do an arbitrary case. So this is a random staircase, right? And let's say this is our path. And the idea is if this is an n-stair staircase, then all of these numbers add up to 1. Because he traverses one step there, then 3 steps, then 3 steps, then 1 step, then 3 steps. And that means the sum of all of these must equal m. So to do a recurrence relation, what we often want to do is break this up into smaller steps. So for example, if we cut it off here, let's say he starts his step with 1 step. So he starts his journey with 1 step. And if he starts his journey with 1 step, then how many stairs does he have left to traverse? It would be n minus 1. So how many ways are there to traverse that? Well, that's given. It's given by an minus 1. So if he starts his journey with 1 step, then to complete the remaining journey, there are an minus 1 ways to do that. Okay, so what are the other options? So remember, this guy has 2 choices. You can ascend 1 stair, or you can ascend 3 stairs. So what if he starts his journey with 3? Well, he's done this step. That's already decided. And now we have n minus 3 stairs remaining. So how many ways are there to traverse that? Well, that would be n minus 3. So in these 2 cases, there are n minus 1 ways to do the one, and n minus 3 to do the other. So in other words, we have an equals an minus 3 plus an minus 1. That's our recurrence relation. So we want to break each valid answer into smaller parts. And that's what we did here. We say in one case there are n minus 3 stairs left. In the other case there are n minus 1 stairs left. Does that make sense? Cool. Alright, so last thing we have to do, find the value of a6. So a6, usually what we do is we just use the recurrence relation to simplify this further, because this is a really hard thing to calculate by itself, so we can express this in terms of previous terms. And that's what the recurrence relation is for. So a6 equals a3 plus a4. So over here we get a6 equals a3 plus a4. And so that would be equal to 2 over here, because we calculated that in part A. But we don't really know this, so let's use the recurrence relation again. So a4... Sorry? Yep, minus 6, sorry. a5. Yep, a mistake. So then we can do a5. a5 equals a2 plus a4. Right, and that's right, and we did that already. That's 2 plus 1. Then this thing, we can use the recurrence relation again. A4 equals a1 plus a3. Then we get a1 plus a3. And so now we know it's 2 plus 1 plus 1 plus 2. And we get 6. And so that's what we have over here. A6 equals 6. We'll do one last question, which is quite similar. So we have a string with 1 and 2 that has some n. So they've given us some examples. This string, it has 1s and 2s, and if you sum them all up, you get 1 plus 1 plus 1, 3, plus 2 plus 2, which is 4, plus 3, and that's equal to 10. So the sum of these is equal to 10. So basically these are some examples of strings that are legit. Okay. So what we'll do now is we'll try to see what they've given us. So if the number of 2's in the string is exactly k, then let's look at that. So we have 2's, how many 2's exactly? Well, that would be k. So the sum of these is equal to 2k. And that means we have to fill in the remaining digits with 1's. So we have 1's, and what does this sum have to be? Well, remember our sum is n, so 2k plus this number of 1's, well, that equals n. So in other words, our number of 1's is equal to n minus 2k. Okay, so in other words, we have k2's and n minus 2k 1's. So the first question is how many digits? Well, that's just n minus 2k plus k. And we get n minus k. How many strings are possible? Well, let's look at this. Remember, we have k2's and n minus 2k n's. So let's just think about that. And then we have n minus 2k 1's. So how many ways are there to basically rearrange these? Oops. How many ways are there to rearrange these? So this can be reduced to a problem, but we have how many spots in total? We have k spots over here, plus n minus 2k spots. So n minus k spots in total. And basically we have to choose which digits or which spots are going to be 2's. So let's see n minus k. Okay, right, because we're choosing k of these n minus k digits to be 2's. So that's the answer to this question. So now we have a different kind of question, where we're letting an being the total, we let an to be this total number of strings with some n. And so we have to find the recurrence relation. So what we did before was we broke this up into smaller parts. So for example, let's take an example. This is a string with some n. So what can we do? Well, let's draw a line there. Now this is a string of some n minus 1. So in other words, if we start with a 1, then we have n minus 1 digit, we have n minus 1, or a sum of n minus 1 left. So the number of ways to complete our string is going to be equal to a n minus 1. Okay, that's good. But we know that's not the only option, because we can't just start with 1. We can also start with 2. So if we do start with 2, then we have 1, 2. That's fine. But what about the remaining string? Well, what's this sum? This sum is going to be n minus 2. So how many ways are there to complete this string? Well, that would be a n minus 2. So in other words, we have an equals a n minus 1 plus a n minus 2. And that's what they wanted us to do. So in other words, we just broke down our string again, and we got this recurrence relation. The next thing they ask us is to find a1 and a2. So this is what we did before. We have to form our recurrence relation, but then we have to do some initial conditions. So let's find a1. a1 equals the number of strings with sum 1. So obviously we can't have any 2's, because then the sum is already 2. So we can only have 1's. And specifically, we can only have 1, 1, because the sum has to be 1. So a1 is going to be 1. Then we look at a2. So a2 is the number of strings with sum 2. So we might have a 1, and if we do have a 1, then the last digit has to be a 1, because they have to add up to group 2. So that's one string. But the other option is if we start with a 2. So if we do have a 2, then we have to stop there as well. So there aren't that many options. We only have 1, 1, and 2. So this will be 2. Right. And it turns out that's enough to define our recurrence relation, so we can move on. So using a and b, or otherwise, prove that this thing is equal to that. So where does this come in? So we might remember C n minus k from part A. Yeah, from this. So what are we doing? We're summing over k. So this means that we're summing over this as k varies. So remember from part A, we said if we have k 2's, then the number of strings, is equal to C n minus kk. Right? But we know that this number will vary because we can have a different number of 2's for different strings. So what we do is we say, let's sum over all different values of k. So k can be equal to 0. Right? If k is equal to 0, then it will be C n 0. That's the number of strings where we have k equals 0. K equals 1. We have C n minus 1, 1, and so on. But how high can we get? Well, let's think about this. Remember our string had n minus 2k 1's and k 2's. So when we did this, we're implicitly assuming that both of these numbers are positive. So in other words, we have n minus 2k is greater than 0, or greater than or equal to 0. So n has to be greater than or equal to 2k. So k is an unfortunate color. So k is less than or equal to n on 2. But k also has to be an integer, so what's the greatest number we can have for k? Well, that would be the floor of n on 2. So in other words, what we're doing is we're summing over all k's up until this max value, which is k equals floor of n on 2. So that's what this side is. This side is summing over all the strings for different values of k. So this number is actually equal to the total number of strings. So this side, in other words, is equal to an. So what we've just shown is that this is an. So you can probably guess what our finishing move is going to be. It will be to show that this is also equal to an. And we have our Fibonacci sequence. And our Fibonacci sequence is defined by a recurrence relation, right? So that means we probably have to use B. So let's use B. So remember we have an equals an minus 1 plus an minus 2. So maybe let's just try subbing in a few values. We have a1 equals, what do we get? We got 1. a2 equals 2. a3 equals 3. a4 equals 2 plus 3, which equals 5. And that's what we got over here. What about our Fibonacci numbers? Maybe let's just draw that down here. And our Fibonacci numbers, they're quite similar. We have f1 equals 1, f2 equals 1. Then f3 is defined as the sum of the two previous ones, which is 2. f4 is the sum of these two, which is 3. f5 equals 5, and so on. And so we can see that there is a pattern, right? We have this thing is equal to that, this is equal to that, this is equal to that. But how do we express that? What we can say is let this equal another sequence. So we already know that Bn, well, it's going to be equal to Fn plus 1. And Fn plus 1, remember, it has the same recurrent relation. So it's the sum of the two previous ones. So Fn plus Fn minus 1. So we want to find a recurrent relation for B. So this is going to be equal to B of something, right? Because Fn plus 1 equals Bn. So Fn will be equal to Bn minus 1. So we get n minus 1 plus b, and then this is the same thing, fn minus 1, bn minus 2. So this will be bn minus 2. So in other words, we do have the same recurrence relation. What about our numbers? Well, we have b1 equals f2, which equals 1. b2 equals f3, which equals, from before we have 2. So we have this recurrence relation, and we have these two starting values. So now we have to compare this with A. A1 had these same starting values as well, right? Because we have A1 equals 1, A2 equals 2, and we also had AN equals AN minus 1 plus AN minus 2. So in other words, these two sequences, they have the same recurrence relation, and they have the same initial values. And we know that because this thing, this recurrence relation, has order 2, because it only goes down to n minus 2, it only needs 2 initial conditions. So in other words, if they have the same initial conditions, and they have the same recurrence relation, they are always the same. So in other words, that means that AN equals BN. So that equals Fn plus 1. So that's how we show that AN equals Fn plus 1. So wrapping up, what do we notice? We showed this is equal to AN, right, using our summing over different values of k. And we showed this is equal to AN using our sequence method. So in other words, they're both equal to AN. And so we would write this out formally. We don't really have time, but we essentially get Fn plus 1 equals this sum, Cn minus k. And so that's from equating them both to AN. And so how do we get that? We basically drew links between the dots. So often when we have long questions, we want to look for how each section leads to the other. So that's how we got this final question. And it's a pretty difficult question. Yeah, so I think that wraps up our workshop there. Unless, should we go on? Sorry? Yeah, okay, we'll wrap up there. Yeah, so that's the end of our workshop. If anyone has any questions in the chat, then obviously feel free to ask them now.
Thank you all for coming.